Hello and welcome back. In this video session, we'll like to examine three different inventory management models that are kind of like known to be in the classical way of dealing with management or the traditional inventory management theories. And what they have in common is that they are, from the lean operations perspective, they are known to be the push models for inventory management. Also, push meaning um, the supplier, the manufacturer, uh, thinks that the customers will need this amount of quantity, and so they will produce this amount of quantity and push it out to the market for the uh, customers to digest, to purchase, to use up the inventory. So that's the thinking, the underlying uh, philosophy, you can say, right? The principle behind these three models. So let's look at what they are actually. So EOQ, right? So starting with EOQ. EOQ is the kind of models that falls under continuous review. So out of the three models, they can be classified into continuous review and periodic review. So continuous review and periodic review, their main ideas are to deal with fluctuations in demand. Okay, so the traditional way of thinking about inventory management is that we have fluctuations in demand, sometimes high, sometimes low, and continuous review. Review here, the word review just means becoming aware of the inventory level. That means uh, becoming aware of at what inventory level position we are at any point in time. So continuous review means continuously in real time. You are always aware of the inventory level. Okay, yes, that's right. You need to track, then you know, because typically a store like NTUC supermarket or even for tire shops, they don't sell only one tire or one kind of good. They sell many different models from different brands, different countries, and for different purposes as well. So continuous review means you've got to implement barcodes, computer systems, scanners, point of sales, databases, IT, networking, and everything, so that at any point in time, if you want to know, you can know, right? So it is assuming that such a monitoring system is available continuously. So continuous review. So continuous review versus periodic review. And of course, now that you know what's review, periodic review is another kind of theory that assumes that you don't need to know continuously the inventory level, only periodically. So every week, then you know that I still have a lot of stock, or oh no, I've run out of stock. So uh, these are very extreme and in a way polarly opposite ways of thinking of how to best manage your inventory system. And remember, the goal for both of them, continuous review and periodic review, are to uh, ensure the fluctuating demand is being met as far as possible. So EOQ is of EOQ model falls under the continuous review model. Okay, and it is for dealing with non-perishable items. So for both continuous review and periodic review, they assume further that the inventory that we are talking about, like tires and uh, car parts and whatnot, are all non-perishable. Perishable doesn't mean rotting; it means deterioration of the market value. So $100 worth of goods, you are able to sell $150. But if it's perishable, that means after some time, after 1 day, after 3 days, it becomes degraded, and so you can no longer sell at $150. You have to sell at $75. So half half. half price to discount sale, or basically it cannot be sold anymore because it has gone rusty, it has rotten, it basically doesn't match the specification. So we're talking about non-perishable items that can last through the inventory cycle. That's good enough. Doesn't have to be forever. So it doesn't have to be 1 year also. It just needs to be able to last through several inventory cycles so that all the assumptions made in the theory, in the derivations, are valid, right? So for example, when you say we have Q items, and after the triangle, we have another replacement of Q items and all that, all these will be valid. Because if it's not, then before we finish selling, we have to like throw away half of them. That's not due to selling, that's due to rotting, that's due to perishing of the goods. And that will make all the formulas invalid, right? Because you don't know when to predict, how to predict the the perishing inventory, right? So that's the problem. So in continuous review, periodic review, they are all for non-perishable items. EOQ is a kind of continuous review that further assumes constant demand, constant rate of demand. That means every day, either the same or different customers will buy exactly 20 tires. That's EOQ. Of course, this is not realistic, but it makes all the calculations and formula derivations very simple, right, and very dependable. And will the result work? Turns out that EOQ model is very robust. That means even in real life, when the daily demand naturally varies, right? So it doesn't vary too much also. So it could be that one day is 25, another day is 15, right? So all in all, average to 20. Sometimes it's 17, sometimes it's 23. So plus minus everything, the overall average is still around 20, number that we assume is the same throughout every day, right? So turns out that it is very robust. What the kind of quantities the formulas uh, predict, they are very usable. They are also very provably optimal. Let's just talk about the cost first, okay? So why is it that it's optimal? That under EOQ, the total annual setup cost. Remember what setup cost? The amount of money you pay to third parties most of the time to ensure that your goods travel through space safely to reach a warehouse. If you add them all up over the whole year, that's your total annual, right? Annual. We look at annual, we don't look at individual. We look at annual. Annually, the total cost, you have to go through some derivation. It's the number of triangles times the per triangle per transaction setup cost. So it's EOQ times that. Annual holding cost for cycle stock. There are two kinds of stocks in your warehouse. They are all the same tires, but they can be partitioned into two categories. The bulk of it is cycle stock. Another section of tires will be what we call the safety stock. Okay, cycle stock, we mean for it to be sold. For example, we think the average demand is 5,000 per year. We will, throughout the whole year, buy 5,000. Correct? Yeah, but that's the average. That's the average. The demand may be 100 tires more or 500 tires less, correct? But we think when we buy the 5,000 tires, that's to meet the average demand. So the cycle stock, when we buy that quantity, 5,000, that's the cycle stock. Why? Because we meant for it to be sold in order to meet the average demand, as opposed to safety stock, right? The section of tires, they're the same tires from the same supplier, right? Equally good, but we keep it aside, we reserve them for meeting emergencies. Whenever there's a surge in demand in an unexpected fashion, not because end of year where we already know that people tend to change tires, buy tires more frequently. No, right? It's beyond our expectation. a sudden surge, yeah, it's more like surge, not drop, right? So a sudden surge in demand that tends to hollow out, empty out our remaining cycle stock if we are unprepared, will now be met because of our little bit of a reservoir, our reserve tires that we call the safety stock. So in general, in principle, we don't sell the safety stock. We didn't plan to sell the safety stock, all right, but we got to keep that. So that's the difference. So the total annual holding cost for cycle stock, because we do plan to sell them, it becomes gradually depleting kind of inventory. So we take the average inventory over the cycle times the holding cost per unit per year. So that's the annual. That means in 1 year, how much money do we pay to hold the average amount of tires? You cannot walk into the warehouse at the start of the triangle saying, "Wow, I have 1,000 tires. My holding cost will be very high." Because if you walk into the warehouse at the end of each inventory cycle, you will see 0 tire, right? So then you might conclude my holding cost is 0, and that's not true. So we find an average level for each triangle and then times the holding cost per unit per year. And finally, we add up the two costs, right? TS and TH, which will result in this U-shaped curve. Now, U-shaped curve has a very unique characteristic. Let me move myself. On the right side, there's this total cost curve. This top curve is the result of adding the linear line, the holding cost, linear to with respect to Q, right? As Q changes, Q is the x-axis. As Q increases, H over 2 is just a constant gradient, right? So as Q increases, annual holding cost increases linearly, but as Q increases, total or annual setup cost decreases as a reciprocal of Q. Yeah, so it is going to be like this. If you add both, you will find a U-shaped curve. So theoretically, in this theory, it tells us that our total cost has a U shape. The thing about U shape is there is a minimum. That's good because it doesn't matter how your U curves here or curves there, it will have a minimum. Therefore, it makes sense to say, how do I achieve this minimum? Because it is minimum for the total cost. Who doesn't want to operate on the basis of enjoying the minimum total cost annually? Who doesn't? I mean, you don't do anything. You just need to choose the right order quantity Q. That's all. So why would you purposely not choose something that's optimal, right? Not, yeah. So that's the contribution by EOQ. We can prove that if you choose the quantity given by the EOQ, which is just substituting annual demand D, your business environment's setup cost, your business environment's holding cost per unit per year, do this math, which is so complicated that it has a square root, but that's about it. And out comes a number. That number, you just need to say it to the supplier every time you purchase. EOQ model says you will then, in fact, it can also prove that you will then enjoy the minimum annual total cost. Any change, if you increase the purchase quantity because you all of a sudden, right, just think that you want to help the supplier. Hey, we are friends, right? So why don't you buy more? So under that kind of moral pressure, you buy 100 more, right? 50 more. Then you will have higher cost, higher annual cost. You suffer, right? But if you buy lower because you think tariff war might affect the environment, let's buy lesser so that we don't incur so much money buying, you end up paying more, right? In terms of total cost. Remember, all the total costs, they are paid to third parties. And it doesn't include the purchase cost. It doesn't include the purchase cost. It includes the interest, right, paid for the amount of money that you borrow. If you borrow money to do this transaction, yes, it does, but it doesn't include the purchase cost because we're assuming no discount. You buy more or you buy less, there is no change in the unit price. If that's the case, then no point trying to buy more just because there's discount. There's no discount, right? So our total cost, something that we are trying to optimize against, will not include the purchase cost. And why would we want to pay more either way, right? By buying more or buying less, right? So that's what the theory is telling us. The other thing about the U shape is the theory, EOQ theory, tells us the U shape is a pretty flat U shape at the butt. So at the bottom here, it's pretty flat. What does that mean? It means that if your EOQ, right, we know we should order 100, but sometimes due to practicality, because boss says so, supplier, negotiates with us, uh, and most likely due to this reason called packaging. We want exactly 100, but it is packaged in terms of either 80 or 120, which is quite a big deviation from our ideal number, right? This pretty flat U-shaped curve, cost curve, tells us that no worries, right? You don't have to argue with the supplier until both faces turn red. At 120, yes, your annual cost will increase by 50 cents a year, or the other way, it might increase by by $1.10 a year. That's not much compared to $80 per year, or $100 a year. So in that sense, relatively speaking, the increment when Q is when the actual order quantity deviates from the predicted EOQ, right, it's going to be minimalistic. It is higher, but not too much in the practical sense. That we are often able to say, okay, fine, I understand, right? Due to packaging, what you want to do. So that's the robustness of EOQ model, right? Remember we were saying constant demand. Every day there will be the exact same purchase of 20 tires. That is not so realistic. But even with fluctuations, with packaging, with forced deviations from the ideal EOQ, it remains to be relevant, or it remains to be quite a good guidance. All right, you don't want to pick 10 purchase quantity. You don't want to pick 200 as purchase quantity. Then where do you start? Well, we know that we can get 100 by just evaluating this formula. That's all. So as you can recall, every inventory management model must give us two formulas, right? Two guidances. One is how many to order. EOQ has given that. The other one is when do we order? And the when do we order part is given by R, the reorder point, which depends on the lead time, yeah? Because L days before we run out of tires, we better start ordering. And if each day the sale of the tire, the demand from our customer is D tires, example 20 or 30, right? Then one day is 20, 5 days for lead time will be 100. So our reorder point will be 100. In other words, as our inventory level drops gradually, 150 to 130 to 110, we don't do anything. But the next day becomes 90, right? So then it crosses the 100 mark, we take action by reordering. So that is the EOQ model, right? So each model must give us two guidances: how many to order and when to. All right, next, let's look at continuous review models in general. The special case is the one we have just covered, the EOQ model, where the triangles are regular. right? So in general means the demand, the day-to-day demand is no longer constant. We allow it to zigzag. Okay, but we make a probabilistic assumption that the daily demand follows, example, normal distribution. Okay, daily demand follows normal distribution. What does that mean? Instead of saying every day is a fixed 20 tires, we say that on average is 20 tires. But every day it is like 21, then 19, then 22, then 20, then 18. No matter what, they center around 20, right? But the moment they deviate higher than 20, there'll be days that follow where the demand will be lesser than 20, so that on average it's going to be around 20. And that's the idea. Also, normal distribution. So that's the assumption. Of course, we'll then give the 20 as the mean, and then the standard deviation sigma, maybe 2, maybe 3, maybe 5.2 or whatever it is. That is appropriate. So we can model the demand. We don't know day-to-day quantity, but we do know the statistical behavior. It's going to show up as a bell curve. Okay, so as a time series, that means as time passes from left to right, we'll see our inventory level deplete. And now the reorder point makes a lot of sense because we don't really know when, as much as timing is concerned, when our inventory level will hit zero. We will never know. It may be the next day because suddenly a customer came by to want all the tires, right, that we have, or it can take 3 months because somehow for no reason suddenly the environment is very slow, right? So we don't know. But what we can tell is the event that our inventory level drops below the reorder point, because we can watch it. And remember, it is continuous review. We already have the scanners, the detectors, the network and whatnot to constantly monitor the inventory level. So we do know whenever such an event happens, right? Whenever the next customer buys some quantity of tires that will make our level fall below the R level, R mark, then we will know and we can take action by placing an order. Okay, so that's the thing. What we want to know is during the lead time, demand during the lead time. So while we model the daily demand as a, say, normal distribution, what we are theoretically more interested in is the overall demand, the total demand over the lead time. So remember the lead time, the 5 days, for example, if L is 5, right? So what we want to know is 5 days demand, not 1 day's demand. 5 days demand. So the 5 days during the lead time. What's so special about lead time? Lead time is like finding a fire in the room. You saw the fire, right? You call fire engine and you call the emergency number, and what happens? The fire keeps burning, and an hour later you have done all you can and the fire is getting bigger and bigger, and let's say the fire engine people haven't arrived. What do? Do you call again? There's no point. They're on their way, right? Maybe not in Singapore, it should be very fast, right? But in bigger countries, it may take some time, right? There may be some roadblocks, there may be some landslides, there may be some resistance on the way or whatever it is, right? So after 1 hour, the fire is very near to you. What can you do? You're very anxious, but what can you do? Nothing. You keep calling. Sending another fire engine from the headquarters? No point, right? Still doesn't help. So knowing that the next time, not this time, right? So let's say luckily you are rescued. The next time you are at your house or somewhere, knowing that if there is a fire or a surge in fire, burning rate or whatnot, it's not helpful to call the fire engine number multiple times. What do? you will plan ahead, right? You will want a safety stock. You will buy a fire extinguisher or a few of them, place it around your house. Why? Because you can then immediately, with almost zero lead time, grab the fire distinguisher and start spraying the chemical, right? At least that will help a lot. Of course, for a serious fire, no amount of fire extinguisher will help. But then, you will have sufficient to meet perhaps an estimated 95% of the kind of fires that normally will be observed around your locality, right? That kind of thing. So yes, so it is the demand. Here the demand is the fire, right? It's the demand during the lead time. Remember the special case of lead time? You have already placed an order. The supplier is on its way, right? But then your demand surges. Your customer suddenly wants to buy a lot. What happens? Do you call the supplier again and order another batch? No point. The previously ordered batch is on its way, right or not? But then, just like the fire engine that's on its way, it doesn't help your current situation. The fire is burning. What do? Thanks to the planning ahead of time. So we model and we devise a formula that takes into account the normally distributed behavior, the randomness behavior during the lead time, so that we have sufficient safety stock, Z times sigma over the lead time. So the parameter here, sigma, is not about daily, but over the lead time period. So if it's 5 days, then your sigma L better be describing 5 days fluctuation, which tends to be larger than 1 day's fluctuation. So demand during lead time is the most important consideration as far as continuous review models are concerned, right? So we look at demand during lead time. Then we need to look at a service level, which is set by the inventory owner. And this service level is not how courteous you are to your customer. Are you having a friendly smile? Did you greet the customer? Not that kind of rating, okay? But this service level is from the inventory management perspective. What's the probability of you having enough inventory to meet the demand? Okay, so that's the probability. That means from 0 to 1 of what? Of you being able to meet demand. That means you have inventory left when the customer comes to your store to meet the demand. The complement of that means 1 minus service level. That means because it's probability, we can calculate the complement. 1 minus service level is the probability of stock out. And physically, it means that what's the chance that when the customer comes to you, you realize you don't have enough tires to meet the demand. You could be left with 2 tires, but customer wants 5 tires, 10 tires. You cannot meet the demand, then you are having a stock out. Because you have to say sorry. If you say sorry, I don't have, sorry, could you wait? Sorry, whatever it is. So you just cannot meet demand, then you have a stock out. And I'd like you to understand that continuous review, periodic review, their main purpose, because now they allow demand to fluctuate. The main purpose is not to minimize annual inventory cost. So you don't see an annual inventory cost being minimized here. We do have a formula. We do have a formula to calculate. So at in this demand during lead time assumption and this setting of the service level to be 0.95, what is my annual cost on average? You can calculate based on the formula, but we are not aiming on continuous review, periodic review. They don't seek to minimize average even annual total cost. So then what are we trying to do? We're trying to avoid stock out. We're trying to avoid stock out and more appropriately trying to manage the stock out. So in a way that, for example, we allow for 5% of the chance to have stock out. So we set our service level to be 95%, right? Assuming demand during lead time follows normal distribution with 100 average tires sold, standard deviation for 5 days is 20, let's say, yeah, and then you calculate, right? So what should be my reorder point? So two formulas are needed. Number one is how many to order. Under continuous review, the formula is copied and pasted from EOQ. Okay, so with two changes. Number one, the demand, annual demand, is no longer D but D bar. D bar just means you take a few years of annual demands because they fluctuate. You take the average and you use that number. Another way is you take several weeks of demands. They differ, right? They fluctuate. You take the average weekly demand and multiply by 52. So in any sense, this is just an average estimate. So the annual demand is no longer a constant, a reliable constant. It's an average estimate. So that's one change. Number two, when we calculate this, we no longer call it the optimal order quantity. We just call it an estimate, a guidance, an appropriate order quantity. Clear? All right, because we cannot prove it, and neither can it be optimal all the time because the annual cost keeps fluctuating, right? The D fluctuates, so there's no way to make it constant. So with these two changes, we basically just reuse the EOQ formula. That's all. Next is reorder point. Previously in EOQ, we use daily demand times L days, which was reasonable because daily demand was a constant and lead time is constant. So we can easily translate L days, we will reach zero stock, right? So L times daily demand will give us the reorder point. In this case, when demand is fluctuating, we no longer can calculate based on a simple multiplication. So what we do is we take the inverse CDF, inverse cumulative distribution function of the service level. All right, so just look up statistics. We don't want to cover statistics here, but it is more the CDF of R. So CDF, cumulative distribution function, CDF of R, if you look at the normal bell curve on the right bottom here, the CDF of R means calculate the area, in other words, the probability from minus infinity until R, right? So that's our usual notion of cumulative distribution function. The probability or the area that is lesser than R on the x-axis. So if that's the case, right, we can talk about inverse CDF. That means if I give you an area of 0.95, can you find out this R right limit for us? And that's the function played by the inverse CDF function. So we give the probability 0.95 and we plug in the function. In Excel, it's norm.imb inverse, right? In R, you can use qnorm to find. So there are readily available software free of charge and all that for us to find inverse here. So very simple. So given 0.95, given 100 as our mean lead time demand, given 20 as our standard deviation for during the lead time, just plug into the formula, right? In Excel, in R, you can find the reorder point ready, and that's it. And then to find the total cost, very simple. Similar, right? Similar to the EOQ annual total cost, except we change the D to D bar, that's one. Plus, we add one more term, which is the annual safety stock holding cost, because we have a bit of a buffer. Where's the buffer? The buffer is over here. So on average, we are buying these number of tires, 100 tires, right? This is to meet the demand during the lead time, 100 tires. But we do buy more. We do buy more. How much more? Z is the Z value, depending on the service level. The higher the service level, the higher the Z, right? Typically, it's 1.96, all the way to 3, and no more than 3. Multiplied by sigma L. So the larger the fluctuation, right? The more uncertain is the demand during the lead time, the more fluctuating it is, the more sometimes very high, sometimes very low, wow, really very wild. The higher such occurrences, the bigger the sigma L, and therefore your safety stock, your little piggy bank of reserve tires better be larger, right? But then it takes up storage space. It takes up air conditioning, humidity control, security checks, everything, because they are as good as any other tire for sale. They are ready for sale, right? So they cost the same amount of protection, holding cost per unit per year. So Z times sigma L, the full amount of safety stock, will attract the holding cost. So even though we may borrow sometimes, right, into and dip our hands into the safety stock to meet sudden surge in demand, two things. We borrow usually a few of them. It's not very common that we hollow out. Not that it's impossible, because everything is probabilistic, but it's not so frequent, not so common. We have very little probability of hollowing out the entire safety stock, like zero. Our piggy bank is zero, right? That's number one. So the depth of borrowing from our safety stock reserve pool is not um, high, very shallow borrowing. Number two, it is also a dent in the safety stock level. That means we only borrow during the lead time. So as soon as the delivery arrives, the first thing we do is to replenish our safety stock first, right? So the time of borrowing is not long, has to be lesser than L. So if L, the lead time is 5 days, maximally you're going to borrow for 5 days, right? It's not going to be very prolonged kind of thing. So the overall lesser holding cost due to the use or the sale of some of those safety stock is not going to be too much. So basically, we just estimate by saying the whole amount of safety stock times H. Yeah, so we're not going to be bothered by minusing 1% here and there, this and that. Okay, so this is the annual holding cost when we are using the continuous review system. So you have three formulas. So remember how many to order, when to order, and of course, cost is always a concern. So we have a formula for the cost. Over here, they say the visual system. In other words, the reorder point can be a marker. It can also be done in various ways, all right, such as to split this into two halves, yeah, and then make it very visual by having two bins, two pails, or two big buckets to hold those tires, right? So that what is supposed to be inside this reorder point here, they are physically separated and put into two, or divided arbitrarily into two parts, right? Two bins, and once we finish up one bin, then that's a very, very clear signal to reorder. So something like this, or maybe the bin can be, one bin is up to a reorder point, another bin is this first part, right? So that when we finish the first part, then automatically that just means it has triggered the reorder point. So whichever way, the idea is guided by the theories investigation of how using the continuous review method can help to meet demand. Okay, continuous review, main emphasis is you need to cope with the fluctuating demand by varying the time of order. So when do you order depends on whether it's early or late that the demand forces your inventory level to trigger the reorder point right now. Yeah. So that's the way it goes. And it locks the order quantity. Every time you order, it's fixed. Now in practice, we don't necessarily become so robotic, right? Like every time we order exactly the same quantity. We become very rigid. And if you're very rigid, how do you cope with a changing business environment all the time? So this is just a theory. The theory is rigidly saying, let's lock the order quantity. Don't change this. So Q is a constant. So tell me a number. So we get a formula. And then the theory says we can cope with fluctuating demand by fixing a reorder point. And this triggering a reorder point will be sometimes earlier than planned, sometimes later than planned, right? Depending on whether the demand is very steep, quickly, draining out your inventory, or very hollow, shallow, taking its own time to drain out the inventory, right? So that's the continuous reviews assumptions. Next, let's look at periodic review. First, let's look at the chart, which is more interesting. The chart here is again allowing for fluctuating demand, right? So we started somewhere, demand keeps coming in, right? And then we encountered a review point, right? Periodic review means periodically becoming aware of the inventory. And in between, we don't know. We don't want to know. We are unable to know, right? Or the boss may say, don't bother me, don't care, right? Or you want to know but unable to know. So because your warehouse is in Indonesia, but your office is in Singapore, right? So if you want to know, you also have to travel down all the way. So you cannot know it every day, every hour, right? So that kind of meaning. So whatever it is, you only count or become aware of the inventory level at the point of review. Let's suppose the review period P is 1 week. Yeah. So every week you go to the warehouse and start counting. Now, of course, the counting can be assisted by computer or whatnot. That doesn't change the fact that only every week then you are interested in knowing this number. Okay, so when you go inside the warehouse and you count, the level is 100. And your target inventory, we'll talk about this in a while, but suppose this target guidance is 300. So that means you have a sale of 200 previous cycle, right? So what you order is 200. Okay, 200. So 300 minus 100. So that's the gap here is your order quantity. Now the next cycle, you enter into the warehouse. You discovered that you are left with only 10 tires. So 300 minus 10, you're going to order 290. Okay, something you start to observe is the order quantity fluctuates, but the timing of the ordering is fixed, right? Because we arbitrarily set to 1 week. So every week we'll place an order to the supplier. So this part is fixed. Periodic review says make the when to order constant. Let's fix that. So when to order is arbitrarily fixed by the owner, 1 week or 7 days. But we cope with fluctuating demand by calculating T. All right. So first of all, we calculate a T based on service level. So T is 300 based on service level. Once you calculated that, we use T to minus whatever we have counted during that point of review. So when we counted 100, 300 minus 100 is 100. If we counted 10, 300 minus 10 is 290. So that's nice because if the previous cycle we sold only 200, then we order 200, relatively lesser, fewer than if the cycle, right, that occurred just before we counted was to have sold 290, more than 200, then we will order 290. We'll order more if we had sold more. Why? Because if we had sold more in the immediate previous cycle, it is not wrong to assume that in the next immediate coming cycle, we would sell more. Not more than this, but maybe roughly around this 290, don't you think? Yeah. So in time series forecasting, there is this thing called naive forecasting, which is to say that you just use the sales done in the latest cycle, latest sampling, and use that as your forecast for the next time season. And naive forecasting says that's the best guess. Right. So in some sense, periodic review has incorporated this naive forecasting in a quiet manner. So it's not that dumb, all right? It is quite clever. In some sense, you just count, you just subtract, and then it has an embedded forecasting ability to say that, wow, previous cycle was high demand, let's order more because next cycle tends to have high demand. So yeah, and if previous cycle only sold 10, then 300 minus only sold 10, then we should have counted 290, right? So 300 minus 290, we just buy 10 because the previous cycle sold 10. What makes you think that the next cycle will sell a lot, right? So we probably buy 10 and that should be the right amount. And so that makes sense. Doesn't sound so arbitrary, sounds so backwards after all, isn't it? Yeah. Okay. So that's the big ballpark idea of periodic review. We have covered most of them. We have talked about when to order, and also to find the T, how many to order, is actually T minus leftover inventory. That's how many to order. But then the discussion becomes, how do you find T, right? T depends on service level. So this formula, inverse CDF of service level, looks very similar to calculating reorder point. So, but please, as an inventory specialist, you should not mix up the terms. Reorder point makes sense only when you are discussing continuous review. The term reorder point. In periodic review, there is no such thing as reorder point. The calculation can look very similar, but that's to calculate target point. It's like the top of the top line, whereas reorder point was the danger zone line, right? Something like that. So the interpretation, the meaning of these two numbers, even though they are both inverse CDF of service level, the interpretations are different. Okay. So target point is the top of the top, the target line. The higher you want your service level, remember what service level? I want to have high chance of meeting my customers' demands, whatever demands they want, whatever quantity they want. Then you better have more reserve. And your target point here better be set at a high number so that high number minus whatever you have counted, you tend to order more, right? For both the cycle stock and your safety stock. And there is also a sense of cycle stock and your safety stock, just like continuous review. The higher the service level, the higher the safety stock, and the higher the target point. The lower, the lower. And you tend to stock out. And that makes sense if you intend to have lower service level. Okay. Why wouldn't we always want 100% service level? I mean, if you open for business, why would you purposely say Well, I like to my customers to have a high 30% chance of stock out. When they come to me, 3 out of 10 customers, I'm going to say sorry to them. Sorry, no more stock. Why would any business purposely plan on having anything lesser than 100%? Well, if demand is actually normally distributed, then to have 100% means you have to have infinite amount of safety stock, which means super high holding costs, right? And even if it's not normal, it will still be logical to conclude that the higher the service level, the higher your safety stock level, and therefore it will take up more rental space, more, humidity control, utilities, security guards, routine administrative counting, and inventory stock taking and all that. Therefore, higher holding cost. And why would you want that, right? So, uh, another reason for service level not needing to be as high as possible is that the kind of inventory that you have is not necessarily so critical. So for example, if you're talking about pharmacy drugs, right? The very common ones, fever pills, right? Paracetamol, cough pills, cough syrups, and all this, which is in high demand quantity because it's more commonly encountered. Then the hospital better have good stock of them, right? And so the hospitals will tend to run these as continuous review because you cannot risk stock out, right? It'll be bad. And what happens if it hits headline news that Singapore General Hospital has run out of paracetamol pills, something like that. That would be very scary, right? Uh, to anyone. So for critical medicine or pharmacies, kind of whatever medicine, right? That's considered important, critical, that cannot have stockouts. Not because you run out of customers, right, for hospitals, but because it'll be very dangerous, it'll be life-threatening, it'll be having a big repercussion in the public or whatnot. Then you want to have high service level. Now, a contrasting example is, let's say you go to the mom and pop shop, grocery store, right? Very dim, not very brightly lit, small little store selling candies, and you ask, sorry, uncle, do you sell Mentos, right? Strawberry flavor. What's the response you get? You go and look. If it's on the shelf, then it's there. If it's not there, then not there. Right now, yeah. And because that kind of shop, uh, very small business, grocery store, right? They tend to run on periodic review, maybe every 2 weeks or every month, because it's candy, right? And say the owner doesn't really quite care, then every month they go and look at their inventory. If it's already stock out, then they reorder, right? Or if there is still stock, they may not even reorder, right? So in that kind of situation, candy, right, that particular flavor, like let's say if it's mint, which is in higher demand, perhaps the review period is shorter, right, every week, so they reorder. But then if it's a very rare kind of flavor or model, demand quantity not very high, occasional, right, then and the shop owner is willing to say sorry to the customer. That means if it's stock out, then stock out. Too bad. I'm not going to like work especially hard just to make sure that the very rare and unpredictable demand is always met. Then in that case, if it's out, then out, and that's what you are told, right? So for less critical um, you inventory items like whatever, right? I'm just using candy so that you understand that it's less critical compared to life-threatening drugs. But even candies, if you're a candy shop, if you're a chocolate shop, then candy is the main thing you're selling, so that becomes very critical, right? So I'm just saying, relative to the stock owner, that thing which is considered less critical, you may want to have less attention, less disturbance, less worry about stock out on these kinds of items. So you then intentionally let the service level be 50% or 70%. Yeah, so it makes sense, right? So just to give you some examples as to why opening a business, right, for their customers, you might not want your service level to be 100% or money, right? So, and if it's not money, then it's disturbances on your attention, shop owner's attention, and that ultimately will result in higher cost. And we want to spend our attention, focus, and time on critical inventory items, not on the less important ones. Okay. And the third formula that you need to worry about is the annual total cost. And so by now you can recognize that all models will give two formulas as guidance, right? When to order, how many to order. And then as a result, there is a annual total cost that will, in the case of fluctuating demand, give us an estimate. I'm not even going to say that it's an average because it may not even be an average. It's just close to the average, because we, for example, safety stock, right? We did account for the occasional borrowing of items from the safety stock, thereby reducing the holding cost a little bit for a short period of time. We just round it up to a whole, right? Yeah, so that's the annual safety stock cost. No change from the continuous review. The annual ordering and annual cycle stock holding costs, they share the same form as as a continuous review, except whenever there's a Q, remember Q, the constant order quantity. That obviously contradicts with periodic review, right? So there's no constant order quantity, but it is being replaced by an estimate. Average daily demand times the review period. Let's say your review period is 7 days. Every day, on average, you sell 10 tires. Then, roughly speaking, the triangle is of height 10 times 7, 70 tires tall. The triangles here, right? The average out triangle, if you kind of regularize them, estimated will have a height of daily demand times the period of review. That kind of meaning. So when we use a meaningful quantity in periodic review to estimate the Q, then basically we just substitute them in, and we should get a good estimate formula for the annual total cost for periodic review. Yeah, okay. All right. Just one more point to touch on, because I just went from the familiar notions discussed in continuous review, right? We were talking about safety stock, reorder point, and all that. And then we come to periodic review. So most of these are similar, like, safety stock and all that, except one minor thing. That is, instead of worrying about lead time, we now extend the period of worry to P plus L. P is our review period, like 7 days. Lead time is L, let's say 2 days. And so our worry time span is a little bit broader. Okay, so 5 days plus, no, what was it? 7 days plus 2 days, so 9 days altogether, right? So our worry timestamp is P plus L, just like what's shown here. P is the review period, example 7 days. L is the lead time, example 2 days. So our worry period, that means fire has started and you cannot call fire engine people twice. So you can only call one time. You have already made the order here. Protection interval is the sum of periodic reviews, review period, and the lead time. Okay, so P plus L is the total amount of time that we will have to worry about. Let's think about it. You come into the warehouse, you counted 200 tires, T is 300, so you of course order 100, right? And then you leave, right? And then you leave. And then you don't know about the review period. And then you do this review, and then you count and you order. Yeah. And basically, the thing is that when we perform the order, there is lead time right now. Yeah. So there's lead time, and lead time days later, we'll receive the order. But by then, we would have left. By then, we would have left. So if in between P plus L, right, we have any stock out, potential stock out, number one, we won't know about it. Number two, we are supposed to place order only during review. Only during review. But when we are at this second review, we are like completely forgetting, no memory, no record of the previous cycle. We go from cycle to cycle. Remember, periodic review requires little to no complicated barcode scanning and constantly knowing the inventory level and networking and IT system and IT personnel. No need. It's a very simplistic kind of infrastructure. All we need is to set the periodic cycle. So P plus L, and once we realize we're out of stock or what, we are just taking care of this cycle. And there's no way that we can patch up or whatnot the previous cycle. If let's say it's sudden big surge in demand, we get hollow out. Most of the time in the previous cycle, it was zero stock, right? We can't do much about it. We can't do much about it. So in order to ensure that we have enough buffer to last until the next part, so the theory includes, right, the L for the next cycle, even though L is covered here, but L into the next cycle is added into our worry period. Also the protection interval. Protect against stock out. Protect against stock out. That's why it's called protection interval. There are times, of course, depending on the businesses, right? There are times when L is larger than P because lead time is just very long. But who will do business with this kind of supplier, right? The thing is, the theory doesn't stop the user of this theory to choose a short review period. So if we review every day and the lead time is a reasonable 5 days, then L is way larger than review period, right? Think about that, right? Or review period and lead time is about comparable, right now. So just when we are about to review, the shipment from the previous order or the beginning of the previous cycle arrives. That kind of thing. And it becomes a bit precarious situation, right? Like if it arrives one day before our review period or it arrives one day after. So in the case when P is kind of unusually short, or L is a little bit long, or just longer, right, relatively speaking, to P, then we might have to start to case A, case B, branch off the theory into two parts, right? When L is less than P, when L is greater than P. So to again make this whole thing very simple, we add the two together. So that doesn't matter whether L is larger than P, P is larger than L. P is larger than L should be the usual, right, normal, healthy way. But if you choose P to be short and L kind of is longish, which is not uncommon, then we don't want to have a new theory. We just want to say, okay, fine, we just add the two together. So when you add the two together, it would have taken care of whether P is less than L, L is less than P. So that would make everything very straightforward in a conservative way. And that is to say that when L is indeed much lesser than P, we may have carried a little bit larger safety stock than necessary, right? But that's a kind of a trade-off. So that just keep in mind. So with that change, that we are more worried about P plus L, then the rest is the same, right? So we just do a inverse CDF of the service level, right? And that is basically saying the target level for P plus L, and that's all. So you just need to make sure that P and L, the review period and lead time, are taken into consideration for periodic review, and that's all. Okay. As a quick summary, looking back at the EOQ model, continuous review model, and periodic review model, you notice that on the left top there's a push. And this is to put this in a ready position to be compared against the lean way of managing inventory. Okay, at which point you will see a pull. So push versus pull. And push is describing the idea that the manufacturer, it could be us, the one selling the tire. We are not manufacturing the tire, but we are the ones selling now. So we are pushing our inventory to our customers. That's the notion. Okay. Why? Because we are thinking that our customers need 5,000 tires every year. So we plan, therefore, based on our review period, based on our chosen suppliers lead time, based on everything, service level, everything, right? So we calculate and have a how many to order, when to order, and total costs in order to achieve this target of annually pushing the 5,000 tires to our customer. That's the thinking. So if the thinking is this way, of course, in real life, when we see that the customer is not buying that many this year, don't know why, right? We will throttle down, right? We will try to sell less. We will try to manage. That's in real life. We'll react. But the thinking behind the theory that kind of doesn't care about all the situational changes, the thinking behind the theory for continuous review and periodic review, and for EOQ, because EOQ is just continuous review assuming constant demand. So continuous and periodic review, they are both based on pushing, right? Pushing our inventory to our customers. The main indicator, of course, is the D here, right? Annual demand, which is to say that everything, all the calculations, all the models is based on thinking about the whole year. But 1 year is a long time. So there'll be fluctuations, there'll be high tide and low tide in the volumes of demands from our customer. We don't quite care nor react to them. We just think about how to push out the annual either forecasted or estimated annual demand tires. Right, that's it. We think you, our customer, will consume that much. We just think of ways to push it out in a way that will, manage our costs appropriately. But we think you need that many means you need that many, right? So somehow or other you buy from us. That's what the theories are assuming, right? At the core level, this is a push thinking. This is a push mechanism. Now in the next video, we will discuss about Kanban system, the kind of pull system that lean operations will encourage us to think about. So I'll see you in the video session.